Testing, okay. Should I just start? Yeah. Okay, hi everyone. I'm Surya. Today I'll be talking about the third work that also does I/O and propositional proof stuff. So today we're going to do more succinct obfuscation via propositional proofs. So our second tagline is how to use PVIO. And hopefully that's like my main goal for today. The first proof is all I hope people will take away, but yeah, let's see. So previously, sorry, this was from a different project. This was, sorry. I thought that was pretty good, actually. Let me show you that again. Okay, anyway, previously we saw PVIO. So in this talk, we can actually take everything that we've seen today as a complete black box. So informally, Chunjung introduced the input length barrier, or the non-falsifiability barrier, and it just seems in general very difficult to construct I/O for Turing machines. So in JJ22, Abhishek and Chunjung constructed input succinct I/O, where the program doesn't grow with input length, for Turing machines. But so that means the program size is polynomial in M and the security parameter. And the security holds for all pairs of programs which have PV proof of the property that M0x equal M1x. And then in Elaine's talk, we saw how to improve it even further to have even better dependence on the runtime. This quantitatively improves our work. We didn't try to actually keep our reductions fine-grained to use it, but that's a total possibility. So in this rest of the talk, I'm going to use PVIO as a complete black box. Yeah? OK. Yeah?
Sorry, again, it has the PV proof, and the PV proof is a constant size, right?
Oh, yes, yes. So I've hidden it here. Technically, the size of this PV proof also contributes to this obfuscation size. Or you can think of it as constant size.
Right.
Yeah. Yes, yeah?
So from what I understand in PV, you can prove equivalence between functions which are written in PV.
Yes.
Okay.
Yes.
So here you are implicitly saying that M0 and M1
are written nicely in PV.
Can actually be described in PV.
Yes.
Then why talk about Turing machines at all? Isn't it the same as
PV functions?
That,
because you can define any Turing machine with polynomial runtime as a PV function symbol.
No. Can you?
Yes. Depends on what you want from it. So you can define a universal Turing machine that's clocked with a clocked runtime that takes as description a Turing machine description, and it will run it for polynomially many steps. So that's a generic way to take any Turing machine and transform it into a PV function symbol. The question is whether you can start actually proving these properties in PV. That might be a different question. But you can take any Turing machine in polynomial time and...
So if you clock it, you can describe
Yes, exactly.
That would be done in general. But
not in general, but as long as you clock your Turing machine, it should be fine. Yeah, great question. OK.
So,
yeah?
So again, so what's the conclusion? Is this for any two functionally equivalent Turing machines?
No, PV equivalent Turing. Any two Turing machines, which you can write as function symbols, for which you can prove that it has a PV proof of equivalence.
But you just said you can...
OK, I said that you can write any Turing machine as a PV function symbol.
Okay.
That doesn't mean you can prove, like, you have M0, you have M1. You translate it into a PV function symbol, and then you can prove equivalence.
But if you can write them in PV, can you just prove it in PV? Isn't that the issue?
No. It might be possible that you can write things that you can't prove, right? Like this is like you can define two functions, you might not be able to prove the equivalence.
I thought it was complete. Okay.
No, it's not.
So the obfuscation algorithm will take the PV description as input, or it takes the Turing machine as input and converts it to PV internally.
No, I think you need the M to be like understandable by the PV proof. So it's like the extended Frege evaluation of the PV function symbol or something. Maybe it's not worth going to that much low level detail in this talk. In fact, I'm going to be doing everything very very abstractly, but we can talk about it offline. Okay. So this work, the goal is succinct I/O to make this thing smaller. And so first of all, I want to try to make a pitch for what PVIO is good for. Secondly, I want to talk about what we can say about succinct I/O beyond PV equivalent programs. And then finally, how succinct can I/O be? Yeah? OK. So succinct I/O is important. I'm not going to try to explain why I/O is important again, but succinctness is important because I/O gives you all these things, and if I/O is inefficient, everything else is inefficient. So if you have succinct I/O, you can solve all these problems, right? So right now, for example, because we don't know how to generically construct I/O for Turing machines, we end up with large ciphertext for witness encryption and large common reference string for snarks. So the running application I'll keep talking about today is witness encryption. So I'm just going to define it. So witness encryption is an encryption scheme that takes as input some instance X star of some language and a bit B, and it outputs the ciphertext. So I'll have a picture in a moment, don't worry. And the correctness property says that any witness for this instance X star can be used to decrypt the ciphertext. And security says that if X star is false, B is essentially hidden. It's like semantic security. So if the definition was a lot, maybe it's easier to remember this picture. So suppose you have a lot of money and you want to give it to whoever has a proof of the Riemann hypothesis. So one thing you can do is you put all this money in a safe and publish a code to the safe. I guess not publish it, but maybe use a witness encryption to encrypt the code to the safe so that anyone who's able to prove that the instance Riemann hypothesis has a witness, which is a proof, can decrypt this. Yeah? And because witness encryption is so simple to construct, I'll just say very quickly what the construction is. You take this program, which takes as input a witness, and it evaluates whether for the statement X star, W is a valid witness. If yes, output the bit. Very simple. And all you do is you throw an IO on top of this. Yeah? So yeah, it's a bit weird because the ciphertext is an obfuscated program. And the security follows from the fact that if there's no witness, B is not in the truth table of this witness encryption, so it's completely hidden. And here, the input length to this witness encryption ciphertext is bounded by, the input is the witness. So by putting a bound on the input length, you're putting a bound on the size of Riemann hypothesis you will be able to support. So in particular, if you use IO as is, you'll have a ciphertext that grows with W. So for example, this means you need to predict beforehand how long your Riemann hypothesis proof is going to be, right? So we do not want this input length dependence. So if you look at implications of PVIO, we have succinct, if you had succinct IO, you get witness encryption with short ciphertext. You also get SNARKs with short CRS. But because you only have PVIO, which works if C0 and C1 are functionally equivalent programs, the witness encryption is only secure if you can start proving that the relation circuit is the null circuit. And similarly, if the relation circuit in the SNARK case is also the null circuit. So you need a PV, so this restriction for IO translates into these restrictions for witness encryptions and SNARKs. And in particular, the takeaway here is this is not all of NP, right? Because this has to be contained in NP intersect co-NP. So this is not everything. And recall, from Chen Zhang's talk, we saw that we can prove a lot of things in PV. So you can prove all these things in Cook-Levin theorem, PCP theorem, and so on. We also showed talked about many constructions of in cryptography having proofs of correctness and being natural. But we do have some limitations. We cannot prove, for example, Fermat's little theorem or correctness of primality testing. So really not everything. And the technical reason for this is one reason is Gödel's incompleteness theorem. The other is the witnessing theorem. So we can't hope to do everything. Yeah?
So
yeah?
you cannot prove Fermat's little theorem. How do you hope to prove Riemann's hypothesis?
It doesn't have to be a PV proof.
It doesn't have to be a PV proof.
For that statement, it could have been a ZFC proof. It doesn't have to be a PV proof.
Oh.
Yeah?
When you have to show that your Riemann hypothesis checking is PV equivalent to a program of 0.
See, I can't because I only have PV-IO. So we want to get IO for all Turing machines, is what you're saying.
Or for your application,
yeah,
that would be...
Yeah, that would be saying, yes, that you can prove that there's no proof in PV. Okay, yeah, something weird will happen. You're right. Okay, so open question from the previous talks. Can we construct succinct IO for all machines? And also, what is PVIO good for? Okay? So this is the big picture, and this is the one slide I hope people will remember from today. So suppose you have PVIO of M0, PVIO of M1. You know they're functionally equivalent, but they're not PV equivalent. What do? So the idea here is to basically say, well, okay, PV alone is not enough for me. I'm going to use PV and cryptography to help me. So for example, I could have one hybrid that says, okay, here's a PV equivalent program to M0. And then, so I'm going to call this M0 mid. I could do the same the other way. But then to bridge the middle, maybe I could say something like, oh, sorry. Oh, I'm missing an animation. Okay, anyway. As a crypto, you can use cryptography to say maybe these two machines are indistinguishable. Okay? This is going to be the general template for a lot of the things that we'll see today. And I want to say, yes, there it is. Okay. I want to say this is actually not a very new idea, and this is exactly what happened in Sci-High Waters, where we wanted to use I/O to do useful things. Where even if M0 and M1 are actually not even functionally equivalent, we could show I/O of M0 and I/O of M1 were indistinguishable by saying, okay, maybe I'll use I/O security here for equivalent programs, and then crypto security in the middle. So basically, again, the idea here, intersperse I/O security with crypto security. So that's like the tagline for today. Yeah? And yes, so this is very much what happened in Sci-High Waters. And so this template itself, I will say, is inspired by both Sci-High Waters, but also this prior work that we had, which showed universal snarks from witness encryption. And I think that'll become clearer in the proof that I will show you in a second. So this is with Zhenzhong, Yael, and Alex. OK, so yeah, in general, our paper has many applications of this idea, where we basically take PV-friendly cryptography and marry it with PV/IO to get applications. OK? So our result 1, succinct I/O for all Turing machines. OK, kind of. So if you have succinct PV/IO, our first theorem statement is that if you have PV-correct succinct witness encryption, you can get to succinct I/O for all functionally equivalent programs. OK? So I define witness encryption as an application of I/O, but here somehow you can use witness encryption to boost PV/IO back to succinct I/O, which is pretty cool. So, and this is a universal construction in the sense that the existence of this witness encryption is sufficient, and you don't need to have it in your hand. So this is kind of like how in Zhenzhong's talk, we didn't need the PV proof in your hand. Here, you don't need the witness encryption in your hand. You just need to know the parameters and that it exists. So what do I mean by PV correct? So I'm saying the correctness of the scheme has the PV proof. So if you write it out symbolically, it will say that for all x and w, if w is a valid witness for x, and that means r of x w equal 1, then decryption of an encryption gives you back the correct thing. Yeah, that's the English way of saying the statement. And I want this fact to have a PV proof. And turns out many crypto constructions are PV correct, which is pretty awesome. And I've set up a couple of examples earlier. And now this is pretty cool, because now we can start using succinct PV/IO to say something meaningful about all functionally equivalent programs. Yeah? OK. So looking back at this picture, if we have succinct I/O, we have all these things. And then in a previous work, we actually showed that witness encryption implied snarks for NP. So if you had short ciphertext for the witness encryption, you also get short CRS for the snarks. But this work, we're saying we can also do that direction. Yeah, you can go from witness encryption to succinct I/O. So from succinct witness encryption to succinct I/O. And if you want to like fully close this triangle, we have to make this additional assumption that the snarks have unique proofs. If you do that, then this work by Chakraborty, Prabhakaran, and Wicks, implies witness encryption. So you can actually get like a 3-way equivalence triangle here, which is pretty cool. So somehow, you can actually go from unique snarks to succinct I/O as well. So if I construct either of these things with succinctness, I can solve this succinct I/O problem too.
This equivalence triangle is like modulo I/O or something, right?
Yes, modulo I/O. Sorry, modulo I/O for circuits. I should have said that somewhere. Yes. Yeah?
Okay, so succinct I/O, you pretty much mean it doesn't depend on the input length, is that?
Yes, input length, yes.
Okay, so you do have like assuming I/O, you have
I/O
a
for circuits.
candidate construction
Yes.
sense.
So the JJ22 construction is the candidate construction.
Okay.
Yeah.
Okay, and then if it happens that the succinct witness encryption
Exists, yeah.
exists, and you.
And we did give a candidate construction we saw this yesterday from Nico's talk. So I mean, certainly this is surprising to me in that when we worked on this, I don't think we thought we also solved the succinct I/O problem. So I think this is a very interesting thing. And so basically now this is an interesting target even just from I/O. If we can construct witness encryption with short ciphertext from just I/O, that is also a very interesting problem. And that solves all of succinct I/O.
What's the relation to the differing input PV/IO route to solving the problem? Like any relation with extractable?
I mean, okay, if you're willing to assume extractable I/O exists, we're already done, right?
Yeah.
Because if extract...
The PCDIO is kind of a
I see.
counterexample assumption. Like it's a
Yeah.
valid assumption.
But it is a knowledge assumption.
No, but if you use PCDIO to go to succinct IO, you have to also use snarks of knowledge. That's the, Although you can first build succinct witness encryption out of it
Yeah.
without snarks of knowledge. Yeah, so
Yeah.
that will...
So what should I conclude about this? Does this This says something about the input length barrier.
Yeah, it says, okay, I'll get to that at the end of the talk, but yeah, it says, again, I guess this is what it says, right? It says that, Chen Zhang said there were these non-falsifiability barriers for snarks and witness encryption and I/O. This is saying it's the same barrier. Break the barrier in one of these places, and we'll solve it everywhere.
If you have a candidate, you believe the barrier can be overcome.
The candidate is from evasive LWE, which we have many counterexamples for, so I wouldn't put too much stock in it. But it certainly means that anyone who breaks the PVIO better be also breaking this construction.
No, but
right?
invisible W is also non-falsifiable.
Yeah, also that. So we want it from standard
Barrier is
assumptions.
always a provability barrier. We believe things exist. Just,
Yeah. But I will say that we didn't have a universal succinct I/O construction before this work. Yeah?
So again, with respect to what you need, so how concrete do you need this witness encryption to be? So the statement there exists, witness encryption.
That's good enough.
So if
And even if you have different witness encryption, yeah.
You need to know how big the ciphertexts are.
how
and
big?
stuff
So
like
you need
that.
a bound
Yeah,
on the
yeah.
ciphertext.
You need the bound on ciphertext, the running time, the PV proof size. So you need all these bounds.
You need one.
You need quantification,
It's not just.
but you only need it to exist. And I guess in a very loose sense, in the sense that, even if I have a different witness encryption that works for each statement, that's actually good enough.
But it,
Yeah?
isn't it kind of globally true because like I/O is best possible? So if you just believe like succinct I/O exists, then you
Yeah, but this is an actual concrete candidate, right?
right. But I'm saying
Yeah.
any concrete candidate is best possible. So if you believe let's say you had a constructed where you
I
need
see.
this encryption, you would get constructed I/O. But then once you know that this I/O exists, any I/O is good enough.
Sorry, I did not follow that.
I don't think
Oh
so.
no. Okay.
Because if you use a bad eye or the usual
I see.
then
Yeah.
you lose the
You need-
influence, right?
Yeah.
To put the succinct dial inside.
I see.
Okay, hopefully
I
that.
mean, but
Yeah.
in reality, the proof will. I mean, that's how we show that the JJIO is actually
Yeah, that is true. Yeah.
universal.
Okay. So this will be the one proof that I'll go over today that I'll go over in full. Maybe I'll say a few other, tease out some other details from other proofs, but this is the main one. Okay. So the goal is to construct succinct I/O from succinct PVIO and succinct witness encryption. So the first thing I'll do is define this new notion of weak I/O, which is actually just going to be a rephrasing of witness encryption, but I think it makes the proof easier to follow. Step 2, I'll show that a PV correct weak I/O plus PVIO equal full I/O. Yeah? So I can boost. And finally, I'll convince you that weak I/O can actually be constructed from witness encryption. And just to make things simpler to follow, don't worry about the succinctness requirements. Just trust me that the succinctness will carry over, so you only worry about the proof. Yeah? Okay. So the first thing I'll do is define weak I/O. So regular I/O, what you do is you take P as input, like some program P as input, and you output some P tilde. And in weak I/O, I'm going to change the order of quantifiers. So weak I/O is actually going to take it. Oh, it's not working. Okay. Oh, it's not working. Okay. It will take as input 2 programs, P0, P1, and a bit B, and outputs some obfuscation, P sub B. So you can think of this as, in I/O, usually at the security analysis step of things, you'll have 2 programs to talk about. Here, I'm going to declare upfront what the 2 programs are. Yeah, that's the only difference here. So in correctness in I/O says that P better maintain the functionality of the original program. And here, I'm just going to say that, the bit B tells you which of the 2 programs I should be equivalent to. So this output program is P sub B. Yeah? Security in the I/O case it holds for every single P1 that's functionally equivalent, right? That's the whole point of I/O. So for every possible P1 that's functionally equivalent, I can show that P and P1 are indistinguishable. The security implies they're indistinguishable. Here I'm going to say something different. I only care about security for the programs that are declared upfront. If P0 and P1 were not functionally equivalent, I don't care if security holds. If they are functionally equivalent, this should be indistinguishable. So all I've done is basically change the order of quantifiers to say that I'm going to declare upfront which 2 programs the I/O should be secure for. Okay? And I'll revisit this, and I'll also show how to construct this from witness encryption. So suppose we have this thing. Yeah? So step 1, fix any M0, M1, and I want to show PVIO of M0 and PVIO of M1 are indistinguishable. And suppose there exists some PV-correct weak I/O scheme. So what I'm going to first say is, if I put the weak I/O obfuscation of M0, M1, and B inside the PVIO, these two things are indistinguishable. So the functionality of this is the same as MB, right? So since O is a weak IO and it has a short proof of this fact, right? So if I have M tilde that comes out of this obfuscation program, I can prove that on every single input, tilde M and MB are functionally equivalent. So that's a weak IO correctness guarantee. And I'm also saying it's PV correct, so I have a PV proof of this fact. So in particular, this means that MB and O of M0, M1B are PV equivalent. So now I can actually use PV IO security. So I can start from, like, our goal was a PV IO of M0 and PV IO of M1. I can do one hybrid and get to the middle here, where I get M0, M1, weak IO of this and weak IO of this with different bits. Yeah? Any questions? Okay. And the point here is basically, we are assuming there exists some nice algorithm that gives us a new algorithm that has the same functionality. And that actually also enabled us to construct a new PV equivalent program to the original program. Yeah? So that's where the crypto helps you. Like, it's a nice algorithm. It gives you a PV equivalent program. So now we have this, and we have to prove the middle. Yeah? We have to bridge the middle. But that is exactly what I said was my weak IO security guarantee. Weak IO said if my M0 and M1 were actually functionally equivalent, then the obfuscations were functionally equivalent. Sorry, indistinguishable, sorry. And ta-da, done. That finishes the proof. Okay? So this is basically exactly the same proof as best possible obfuscation, as he said. So yeah, this is going to look like the same proof that Rachel showed on Monday. And it works with witness encryption, this weaker notion of IO. Yeah? Okay, finally, I have to, so the edge here, I use PV equivalence, and in the middle, I use weak IO security or crypto security. So finally, I have to convince you witness encryption implies this thing. So first, I'll give a construction that is correct, but not secure. So the weak IO obfuscation is going to output just P0, P1B as is, okay? To evaluate it, I'm going to first check, okay, is P0 and P1 equivalent on X? So you're basically on the fly, as you get the input, checking if P0 and P1 are equivalent. If yes, I'll output P0 of X. Else, I'll output PB of X. So unless you give me something where they're functionally equivalent, I will only be running the first line. Yeah? So this is correct, right? But this is clearly insecure because I wanted to hide B. So I only want to give you a way to access B if P0 and P1 were in fact not functionally equivalent. So I need to hide a bit, given a statement P0, P1. So this is exactly witness encryption. So the final construction is basically the same thing, but except instead of giving out B, I'm going to give out a ciphertext encrypting B. And to evaluate, you'll check if P0 and P1 were equivalent. If yes, then sure, I'll just output P0 of X. It doesn't matter. If they're not equivalent, then I have a witness that proves to me that P0 and P1 are not functionally equivalent. I can use it to decrypt and get out PB of X. Yeah? OK, so that's the whole proof. Any questions? And also, I think it should be quite easy to see that if the witness encryption had a proof of correctness, this also has a proof of correctness because this is a very simple use case of it. Yeah? OK.
So it's just a recipe for bypassing the non-falsifiability.
Mm-hmm. Yeah, but it's somehow like
it's an exercise.
Yeah. It's like saying that if you bypassed it in the witness encryption, you've done it for everything. Yeah.
The way you do it, that's also not black box or whatever.
Yes. Of course, it's not black box at all because I need this PV proof of correctness. Yeah. But yeah. So hopefully I've convinced you of this new template of just using the PV plus crypto. We'll do more with it. So now, okay, I've hopefully addressed these two goals a little bit, but we'll talk about the third goal, which is can we construct even more succinct I/O? So again, if that was how it would look. Okay, so motivation for this is, again, I'm going to start with witness encryption and say I want succinct or witness encryption. So what do I mean? So even if I had input succinct I/O, if I obfuscated it, this will grow with the size of the description of this machine, which grows with the relation circuit and the statement X star. But if you think about witness encryption, the amount of things that you're trying to hide in this witness encryption is very small. It's just 1 bit, right? So maybe you could have this different way of doing it where I let this program be public, cut out the secret that I actually care about hiding, and obfuscate the secret separately. So if you've seen succinct garbling, partial garbling, this kind of looks like that. So yeah, like why can you kind of like take the program and put it into two parts, one that's public, one that's private, and somehow do obfuscation that way? So this is the motivation, yeah? And hopefully then you can say, this obfuscation here is only poly lambda because all of this was public anyway. So everyone knows the Riemann hypothesis. So I don't need to pay for that in my obfuscation size. Okay, I don't know the Riemann hypothesis, but it's okay. So the new notion that we propose in this work is this notion of being succinct in the description of the program. So suppose you can take a program and it has a public M and a secret SK. I want to be able to cut out the M. Oh, sorry, this is lagging. I'm gonna just use this. Okay. So I want to be able to cut out the secret key and obfuscate that separately. So correctness says, okay, I'm abusing notation a little. Think of this as like an obfuscation evaluation algorithm that uses the obfuscated k hat. Yeah. So correctness is, the usual thing where M sub k hat is the same as the original program. Security says that if I have two SK and SK prime, like two secret keys, for which for all x the two programs are equivalent, then M k tilde and M k prime tilde are indistinguishable. Yeah? So basically, as long as the secret part gives you the same functionality, I should not be able to tell the two obfuscations apart. And the key point here is that this has to be succinct. The k tilde only grows with polynomial sk and, I guess, security parameter, but not m. So this is a new notion that we propose. And yeah, so this is a new frontier, fully succinct I/O. Can we do it? So the first theorem we show is actually you can take JJ22 I/O black box and boost it to be fully succinct PV I/O, assuming just LWE, actually. I didn't say that. Yeah. So that means, again, we have this like PV restriction that I need to be able to prove in PV that the two programs are functionally equivalent. But it's fully succinct in the sense that it only grows to the size of k. And as a corollary, we actually get fully succinct PV I/O from I/O for circuits and LWE. Okay? So what's the construction? It's very simple, and it's probably the first thing you would try. Hash and obfuscate. Hash the machine M, which is the public part, and obfuscate the program to check against the hash. So the point is I'm going to start feeding M as part of the input instead of baking it into the program. And because this is a PV/IO, which is not going to grow with the input, it's not going to grow with M. So I'm just going to obfuscate this with input succinct PV/IO. Yeah? And again, to reiterate, it doesn't grow with M because that's now an input. And yeah, that's the construction. That's the whole construction. It's very simple. But prove security is completely unclear. Okay, I have a skip button if, okay, do I have time? Oh, I have time. Okay, security, programs aren't even functionally equivalent, right? Because if I take the two programs that I'm obfuscating for SK and SK prime, if I find any hash collision, so if I find some M star not equal to the original M, where the M star SK and M star SK prime are not functionally equivalent, then these are not functionally equivalent programs. Yeah? But the idea is to use PV-friendly somewhere binding hash. So this is the same SSB that Elaine introduced, and succinct garbling techniques. So this proof is a little, it's a lot. So I'll just give a flavor of the argument by giving like one step of what the hybrid would look like. So what's a somewhere statistically binding hash? So it's a hash where there's a trapdoor mode where I can generate the key along with the trapdoor in a way such that a regular untrapdoored key and a trapdoor key look indistinguishable. And any hash will be binding on index I. Yeah? So usually, this is known to be a very I/O-friendly object, and why? Assuming I/O, here's what you might try to do. You will switch from sampling HK to HK sub I. Then you might try to hardcode the following check. I'm going to introduce a line in this program that says I'm going to check that M star of I is exactly equal to M of I. Right? This is like because now the hash key used for this hash is binding on I, the only thing that will hash to H will also be equal to M on I. Yeah? So this is a functionally equivalent chain, so you can use I/O. And then you might switch HK to be binding on a different index and so on. Okay. So we used IO here and we used crypto here, like in the other two hybrids. But now we only have PVIO. So yeah, so PVIO, so now you have to think a bit more about how are you going to argue that this is functionally equivalent, how do you reason about this functionally equivalent change, right? And so that you can actually show it using PVIO. You would say, well, okay, if I extract this hash, I'll get M of I. And the fact that the hash of M star is equal to H, and these H's are the same, means that the ith bit of M star must match M of I. This is how you would try to reason. If you wrote down this proof of functionality equivalence, this is what you'd write down. And turns out this is, you can abstract out this property from many SSB hashes as being a PVIO-friendly SSB. And you can just abstract it out and use something like that instead. Does that make sense?
Being PV-friendly means
you can
prove these things using
PV.
For that SSB construction.
Yes, and I only did it for one, which is like I took the rate 1 OT from LWE and did this. I guess you can also use the FHE construction and do this, but you should be able to prove this property for those constructions specifically.
Now what does it mean you have, sorry?
Yeah?
Then the size of U grow if you add more constraints.
Yes. So this is a flavor of the argument, not the argument. So I just wanted to show what you might try to do in this argument. This is one type of argument, one type of hybrid I will make in this proof, but this is not enough. Yeah.
I guess I was asking the same question. I guess here, what does it mean to continue 4 and 5?
I mean, I'm just saying 2 to 4 might be doing this, but then I'm not saying that 1 was hard-coding everything before. But basically, again, exactly because of this point, we cannot hardcode every bit of M, so this is not what we're going to do. So firstly, we need even more properties from this PV-friendly SSB. We need it's constructed in via a 2-to-1 SSB specifically. I won't go into it because it's a bit technical. But the second thing is I need succinct garbling techniques. And succinct garbling, the whole point is you can do careful pebbling arguments to order the hybrids cleverly to avoid this space blow up. So I'm saying this very abstractly. The actual proof is quite technical, but the point is these things are very PV friendly. So therefore, I can actually do them from standard assumptions. Yeah? OK. So now that we have fully succinct PVIO, what can we do with it? Turns out this notion alone is sufficient to construct computational secret sharing schemes for monotone circuits with the URs of size at most n, sometimes you can improve on n, and individual share size polylambda. And turns out this fully succinct notion that we abstracted out here is exactly the thing we needed to get around the so-called representation size barrier in computational secret sharing, where the issue was that it seemed like every construction for some reason had dependence on the size of the publicly known access structure. But here, because we can treat it as public in this fully succinct PVIO, we can immediately get around this issue and we overcome the representation size barrier. And previously, the share size grew with some parameter on the number of gates in this monotone circuit. And I would like to say, yeah, this was also concurrently achieved by work by George, Shafiq, and Brent from IO and injective PRJs, I think. So the assumptions are slightly better. But yeah, our constructions are completely different, which I thought was pretty interesting. The one thing I want to point out here is the final thing that we achieved out of this theorem statement had no reference to PV. All I'm talking about is monotone circuits, and that's all I said. And somehow fully succinct PVIO was good enough for this. And the reason for this is that our theorem is actually quite general and works for any natural monotone function. I'm just coining this term, for which you can prove that the function is monotone. So what does that mean? That means if you give me a subset S of t, and I know that f of t was false, then f of s is also false. So you can prove that this function is in fact monotone. And all you need is the fact that this has a PV proof. And so one other corollary we get, for example, is that you can get a succinct scheme for bipartite matching. this is interesting because bipartite matching doesn't actually have a monotone circuit like a polynomial-sized monotone circuit representation. And here we also get improvements because you can prove Hall's marriage lemma has a PV proof, which I thought was a very funny thing I ran into, and Cook had already proved it for me, which was pretty awesome. So yeah, and I really don't know how to derive this kind of thing without like abstracting out to the layer of PV proofs, because I think it will make the hybrids very complicated if you try to do it directly for bipartite matching or other complicated monotone functions. So I thought this was really cool. And I thought, I might as well try to sketch out why, because this is such a simple proof, I might as well sketch it out. So how do you prove monotonicity of a monotone circuit? So depth 1 is very easy. Yeah, a monotone circuit only has AND and OR gates. So for depth 1, you have an AND or OR gate. You just check that it's monotone, and you're done. And suppose you have depth D. Yeah? This induction. So suppose you can prove for depth D. Then you can add a new layer of gates here. And you can prove that if I put S and T as inputs here, the output here will satisfy the fact that if S is a subset of T, S prime is a subset of T. Yeah? I can just prove the output of this layer is going to be monotone. So now I have S prime and T prime, and I'm going to run this depth D circuit on this, and we've already proven it using induction. And yeah, you might complain that this was not the same induction Chantang showed, but we only care about D, polynomial size D, so that's actually okay to induct on D. Yeah? And it turns out you can actually formalize proofs like this in PV. So I just wanted to give a flavor of what this is. Yeah? Okay, and our third result, maybe it was fourth. Okay, I'm not sure. And it's definitely not theorem 1. Is that, again, just like before, this fully succinct PVI is also universal. And for this, either fully succinct witness encryption sufficed. Oh, the animation order is a mess. Oh, or almost fully succinct unique snark. So here, we couldn't quite get it to work with fully succinct unique snarks for some technical reasons. Basically, you have to start you have to hard code the instance at some point. So it's a hairier definition, but yeah. But these three are actually equivalent definitions, turns out. Sorry, equivalent up to I/O. And so yeah, again, for fully succinct PV/I/O, we can get a nice equivalence and universality result.
Well, I'm sorry, what is this almost, what is it pointing at? Like, is it just...
Just the kind of snark that you can get from I/O. It's not...
Yeah. It's
okay, so
it's not fully succinct. It has like a long URS, but that's a short structured part.
Okay, so it's a weaker assumption than the almost fully succinct. Sorry, from fully succinct to
yes.
Okay.
Yeah.
I see.
Yeah, I would love to get rid of that assumption. So that's a great open problem. And again, it's kind of interesting because I motivated this notion of fully succinct I/O by showing you this picture. But somehow this work shows that this, again, are equivalent notions, which I think is pretty surprising. But OK, finally, I'll conclude with a few more applications to get assuming fully succinct I/O. So no PV here. I just want to say that this abstraction seems very important and interesting without any PV implications. But the first thing you can show is rate 1 I/O from any program. So that means the obfuscation size is really just rate 1 in the size of the original program. And we didn't know how to do anything better than rate 2 before this work. And one example that is, for example, a null circuit. And for null circuits, we can get rate 1 I/O. And a few more. And best previous thing that we knew was rate 2 by this work of Prabhanjan, Abhishek, and Amit. And so yeah, the fully succinct I/O abstraction gives the rate 1 very easily for zero circuits. And another one, so this one is a bit more complicated to explain directly, so I'll try to motivate it. So has this ever happened to you? You have two programs, P0 and P1, and you can show I/O of P0 and P1 are indistinguishable. But you have to go through some horrible middle hybrid that's gigantic. Yeah? So you have to pad some intermediate circuit to be really big. And so then that means your I/O has to grow with the intermediate circuit. Yeah, this is a phenomenon that happens in many I/O proofs. I see a lot of nods. Yeah, I heard I related to the audience. Okay, so this means the obfuscation has to grow with this middle thing, which is a bit annoying. And it turns out Justin Holmgren actually showed that this kind of padding is completely necessary. So, okay, you need it. Can we at least do something better? And so turns out you can in our work, we show we can pad with a uniformly random string. So an obfuscation can look like this. So you IO P0 with a gigantic URS, and it will be indistinguishable. And the URS here is going to be basically the padding. So like the way to think about it is, okay, fine, you need this padding, but it can be completely unstructured. And that's, again, a very nice thing that comes out nicely from this fully succinct IO abstraction.
So what is URS?
A uniformly random string. I just abbreviated it. So you can take any, so the heuristic says basically, you can take any uniformly random string you see in the sky that you like, hash it, put it in your obfuscation, and that's enough for you to publish your program.
So it's reusable across.
It's reusable, yeah.
But the problem, we have to use it to run.
Yes, to run it, you need to use it. But there's a very simple heuristic you can use to get rid of this issue, at least at obfuscation time. Okay. Yes, so in this work, again, we showed this very nice triangle. So the way I like to think about it is like, there's these three dragons, which are basically like separate non-falsifiability barriers that you can define for each of these objects. But our work says, you know what, they're the same dragon. They're the same problem. And it's like, and I don't know how to make such a statement without PV, which is very interesting. So that's one interesting open problem where, can you show these kind of equivalence without using PV? And yeah, so open problem is slay the dragon. Yeah, like it's just one dragon. It's not three anymore. Okay, so summary of our work. This is the original title of a note suggested for my thesis, but I rejected it. So I'll put it here. Succinctness and propositional logic. It really seems like a match made in heaven. It seems like propositional logic is meant to give us succinctness. So how much more can we leverage this? So we showed how to use PVIO, and we showed, you know what, the JJ22 construction was already universal. And we also pushed the level of succinctness we can ask for, and we asked for full succinctness. We also gave it nice applications of that. So yeah, and a new interpretation comes out of this, which says, succinctness is really the same problem across all these difficult cryptographic objects. Okay, let's slay the dragon. Yes. Okay, thank you.
So in all these PVL constructions, can you prove in PV that M is equivalent to PVL of M?
I wrote a proof, I think, right? We wrote a proof in the appendix of our paper. You're saying does the JJ22 IO construction have a proof of correctness, right? That's what you're saying?
No, the proof of correctness should be in PV.
Yes, yes, it is. Yeah, over multiple works, we've proven things like FHE, garbled circuits, all of this have correctness, and if you put them all together correctly, it does. Yeah?
You have better abstractions to write these PV and EF because I feel like...
Yeah, so... okay, I don't want to put burden on him, but Jatu is currently... he actually held a reading group at MIT and wrote a bunch of really nice lecture notes that he said he was going to make public at some point. I think that would be a great starting point. Hopefully this paper... What?
So pressure.
He's already written it. Yeah.
But is that...
I know.
Your paper also...
And this paper hopefully has a lot more examples.
You can also just read your paper, right?
Yes, we can also read my paper, which will be online soon. But no, I genuinely, I want to thank Jatu a lot. He's not here, but he really explained a lot about PV to me, and I think his lecture notes were my starting point, at least.
Even with EF, it's very difficult to write without higher level abstraction.
Yeah, that's why most of the proofs that we write in this paper are very high level. I think it's like the same thing as saying, your Turing machine description is also very high level, right? You're not writing x86 code. It's the same level. There's some level of familiarity we need to get to the point of being familiar with the abstraction. But modulo that, I think our paper is a reasonable place to start. Yeah.
Back to your dragon picture with that.
Yes, of course.
That was funny. It's more than arrows than that. Okay. I see. So I got the witness encryption to succinct IO, that orange arrow, and then the unique snarks with.
It's from a prior work.
Unique snarks.
To
succinct IO. Which one was?
Oh, so unique snarks to witness encryption, I think only assumes
No, I'm sorry. The orange arrow on the bottom left. Yeah.
Oh, that's by combining these.
Oh, okay. So you didn't do. I didn't.
No, we're just combining the. Yeah. Yeah.
Those together. Okay.
Yeah. I'm just saying, as a corollary of that line and this line, you get this line.
Okay, so that one you didn't show directly. You just.
Yeah.
In the fully succinct.
Yeah, in the fully succinct case with the almost
You
succinct
have to redo the
triangle. Yeah. Because there's like some because we don't get
unique
yeah.
smarts to witness encryption in the fully succinct setting requires a read through.
So we have a hike that we'll leave in 10 minutes. It's like, I don't know, 3 miles.